This video covers section 9.2 of the CIE 9618 Computer Science A-Level specification. This is algorithms. So first of all, we need to know what an algorithm is. Our definition would be an algorithm is a solution to a problem expressed as a sequence of clearly defined steps that, if you follow it correctly, will produce the required result. So algorithms should be finite. They must terminate after a limited number of steps. They shouldn't run forever. Unambiguous. The steps should have only one possible interpretation. They need to have well-defined inputs and outputs. And they should be effective, i.e. each step must be simple enough to actually be carried out. So a very basic example would be making a cup of tea. We follow algorithms all the time, for example in cooking. So fill the kettle, boil the water, put the tea bag in the cup and so on. These are just a sequence of steps that, if you follow them correctly, should result in a good cup of tea. And we can represent algorithms in various ways. We can use structured English, pseudocode, or flowcharts. But the underlying sequence is still the same, regardless of how we describe them. So when we're doing this kind of algorithmic design, we should be using good identifier names. And we need to be able to write them into an identifier table. So what makes a good identifier name? This is things like variable names and function and procedure names. So anything that you choose to name within your program should have a good name. Now, meaningful means the name describes what the data represents. So for example, student mark is meaningful, but X is not. Each one should only have one purpose and hold one kind of data. It should be written in a consistent style. For example, if you're using camel case, then use that consistently throughout your program. You shouldn't have spaces or reserved words in your identifier names. They'll break the rules of the programming language anyway, and you'd get syntax errors. And it shouldn't be misleading, so it should never give the wrong type or the wrong purpose. And then you write these into an identified table. So that table represents, for every piece of data, the identifier name, its data type, and a short description of what it's for. So sometimes you see this called a data dictionary, or in this case we call it an identifier table. So when writing algorithms and then that lead on to programs, we have three main program constructs. And you can think of these like the building blocks of all programs. And they are sequence, selection, and iteration. In sequence, statements are just executed one after the other in the order they're written from the top down. So you can see there we just do input length, input width, and then we keep going down and down and down until we get to the last line that was written, and then it stops. The program on the algorithm is finished. That's sequence. And then number two is selection. So in selection we can choose one or two or more branches. So in that example we say if the mark is greater than or equal to 50, then we do the first part, which is output pass. Otherwise, if it's not true, then we output fail. And there are various ways we can implement these kind of selection constructs. There's if then, else, end if, and there's case of, end case. Then we've got iteration. So in iteration, a block of statements is repeated. It could be repeated a set number of times or until some condition is met. For those, we've got three things normally in pseudocode. We've got for loops, while, end while loops, and we've got repeat until loops. So in selection, we can use if or case, and in if we can have a two-way branch. So we use something like if, else, end if. This is all CIE pseudocode format, so it may vary in different forms of pseudocode, because one of the things about pseudocode is, although it's very much like program code, there is no fixed set of rules or syntax for it, so it does vary. But CIE have a standard that they use in their exam papers, and this is the kind of thing they write. And then on the right we've got a case instead. So when we've got multiple ifs and a lot of tests on a particular identifier or expression, if can get quite long, so we can use case instead. We can only use one identifier or one expression for the case, but we can have multiple values of it. So in that example on the right there, we input move, and then we do case of move, and it could be they press the W, the key, the S, or the A, or the D, and all you do is the condition that you're looking for, i.e. that move was W, follow that by colon, and then write whatever code you need. And you don't just have one line of code, you can have as many lines of code after that as you want before the next value and a colon. You can also have an otherwise at the end, and that means if it's none of the above, then it just does that code instead. It's an optional piece of code. You don't need the otherwise, but if you want to do something when none of the other cases are true, then you use that. And going back to the if end if for a moment, you can nest them. So in that example at the bottom left, we have an example where we're putting an if inside an if, and you just have to follow the logic from the outside inwards, so from the outer level all the way in. However far the nesting goes, you just carry on going in and in until you get to the logic that will actually be resolved as true, and then nothing else is done after that. So once a condition is true, it's met the condition, and it does that code, then none of the other code will be done. So the else will not be done, and any other part outside that will not be done. Then we've got iteration. So as I say, we've got several ways of doing it. The for loops is otherwise known as a count controlled loop. It's a definite loop. That means that we know how many times it's going to execute. So if we say for count is 1 to 10, then we know it's going to do it exactly 10 times. And we use this kind of loop when we know how many repetitions in advance. So before we come to that code in the program, it will know how many times it needs to do that. And then we've got two other types which are condition controlled. There's pre-condition controlled and post-condition controlled. Now the precondition means that we test before we go into the loop, and that's implemented in pseudocode with the while. So we say while the number is greater than 9, do something, and then end while. And because the condition is checked before we go in, we may never do that code in the body of the loop. Okay, so if that condition is never true, even from the beginning, we don't execute the code. On the repeat until, it's called a post condition because we check the condition at the end. So in this case, we're asking for a password and checking the password, and it does the check at the end of the loop rather than the beginning. That means that the body will always run at least once. Now in pseudocode you can use either one of those, you can swap them, but sometimes one is more obvious than the other for a particular problem, but you can make them both work. You just have to rejig the code a little bit to fit which one you want to use. And bear in mind that the logic condition would be the opposite when you swap those round. So for example, if we took the while number greater than 9 end while and said we wanted to do that with a repeat instead, we'd have to say repeat until, And instead of saying number greater than 9, we'd have to say number is less than or equal to 9, because that's the logical opposite of greater than 9. So input and output. To get a value in from the user, so when they want to type a value into your program, we use input followed by an identifier, i.e. a variable name. So for example, input answer, they type something and it will go into answer. And in CIE pseudocode, the data type of that is whatever the variable was. So if you declared answer as a string, then you would get a string. If you defined it as an integer, you would get an integer. And then output, you just say output and the value or values that you want to put out. You can put out literal text in quotes, you can put out variables, or you can put out combination of things if you separate them by commas. So on the right there's an example. It's good to output a message before you ask for input so they know that your program is expecting something to be put in. And then we use the if condition check to see if the value is greater than or equal to 50, and we output the appropriate value. So input output is quite simple in CIE pseudocode. Now we can express our programs using structured English, and structured English is just a way of documenting algorithms using ordinary English, but with very similar structure to our algorithms with sequence, selection, iteration as the program constructs. So when we write it, we write one instruction per line. You can number them for reference. Use selection, iteration, use the same kind of keywords like if, then, else, while, for, repeat, and so on. Put them in capitals makes it a little bit more obvious. Everything else is basically English. There isn't a strict syntax for it. You don't need particular punctuation or variable names. Indentations used to show which lines belong inside selection or loops, in the same way that we do with pseudocode. So on the right there we've got an example. So a customer buys an item. If they have a discount code, they get 10% off. Otherwise, they pay full price. Ask for the price and code, then display the final price. So this is the kind of thing you might get in an exam where they just give you a problem in English, in everyday English, and then you've got to convert that into structured English. So you break it down into steps, you describe the steps, and you use the same kind of constructs as you would for pseudocode and programming. So we can convert that to structured English into pseudocode, and for CIE, of course, you need to declare your variables, give the data types, and then you'd be using output and input for the I/O, and using your if, end if, and so on to do the actual program code. Alright, flowcharts. So flowcharts are another way of describing algorithms. They use shapes and a visual representation of the algorithm. The first shape we're going to look at there is the terminator. We always have a start at the beginning of the flowchart, and we always have at least one stop. So it is possible to draw the diagram with a single stop and make the lines all go to that one stop, but sometimes it's easier just to draw multiple stops. Then we have a parallelogram for input and output. So whenever you do an input pseudocode type command or an output command, then you would do those inside a parallelogram. So any displaying on the screen or getting information from a user would be in a parallelogram. A process represents any action really that isn't covered by one of the other shapes. So if there's anything you want to do, like incrementing a counter, assigning values, changing something, then it's going to be in a process. And then a rhombus, or some people called it a diamond, but a rhombus shape is a decision. So this is where we can check some condition and branch. So we're going to go one way or the other. We can only go one of two ways, and we label the outputs from that as yes or no, or true or false. So if the answer is yes, we go one way, we flow one way. If the answer is no, we flow the other way. And then we have the rectangular shape, which is like a process, but with two lines down the side. And that means that it's a predefined process, i.e. it's a function that was written already, or you draw on the flowchart for that somewhere else. And you're just reusing it by calling it here. And then the whole lot is connected by arrows. They can only ever go in one direction, and you can never have an isolated shape that isn't connected to the others. So make sure that the flow can go all the way from the start, all the way through any possible route, and finally end up at a stop. So just recapping the rules then, you must have at least one start. You must have one start and at least one stop. The process input and output boxes all have one arrow coming in and one arrow going out. Decision boxes can have one coming in and two going out. Every symbol is connected. Loops must be able to end, so don't draw flowcharts with infinite loops in them. And the flow can only go in one direction. Here's a basic example showing sequence, the program construct of sequence. We start, get the input for the length and the width. Then we do a calculation in a rectangle, which is process, and then we output the area in the parallelogram. Remember, all the input and output is done in parallelograms, and then we stop. So the pseudocode to match for that flowchart is there. Input length, input width. Area is length times width, and output area. Here's an example for selection. So we start, we input the mark, and then we do our rhombus to make a decision. So we say, is mark greater than or equal to 50, question mark. So you're basically asking a question that you must be able to answer as yes or no. And then if it's yes, if the answer to that question is yes, then we go to the right. If it's no, we go to the left. But then, as you can see, we rejoin again. Eventually we must get to stop. Everything must eventually get to a stop. Here's an example with iteration. So we start, we set a count to 1, and then we do our test, our decision in a rhombus. We say, is count less than or equal to 5? If it is, we output the count, increment the count, and go round again. And see, we're back to the decision, and eventually we will get to the point where that is no longer true. Count is no longer less than or equal to 5, so we branch off to the no and stop. And in CIE problems that you get in exam papers, you will often see that you're calling a function, you're getting a result back. And it's usually done like this. So you do some code first, you'll do some steps in your flowchart first, then there'll be a call to a function that will produce a result that you need to store. So you put the result in a variable, and then you move on to the next step, and you can start using the result that you got from the function. So whatever you store it in, whatever variable name you store it in, the actual variable name and the call to the function go within the rectangle with the lines down the side, and then it can be used after that in any subsequent shape that you're using. Now, one thing they want you to be able to do and describe is stepwise refinement. So stepwise refinement is expressing an algorithm through successive levels of increasing detail. Each level rewrites the steps above it in more depth until every single step is single, unambiguous, and precise enough to be turned directly into code. So key points are, it's a top-down process. We start broad, we start very basic, and then we refine it further and further and further. Nothing's lost between the levels, each step is just expanded, not replaced, and refinement stops once every step is simple enough to code directly. It is related to decomposition, but it's refining the steps of one algorithm rather than splitting a problem into separate modules. So in our worked example there, we start with a broad statement, find the average mark of a class of students, and then we're going to refine that a little bit further. And we might say it requires these 4 steps: get all the marks, add up the marks, divide the total by the number of marks, and then display the result. And then we might need to go further, so get all the marks needs a little bit more refinement, so we break that down and show that that'll be done in a for loop, and so on. So we just break it down, more detail each stage until it's trivial to turn into code. And in your algorithms, you will need to be able to use logic statements and to combine conditions to make compound conditions with Boolean operators. So we've got and, or, and not we can use to combine things. So and means both things have to be true for the condition to be true, or means either of them need to be true for the condition to be true, and not inverts a value. Okay, so we can say things like repeat until end of file, or we could say while not end of file. Alright, so that's the end of section 9.2, an introduction to algorithms and using meaningful identifiers, using program constructs, and expressing algorithms in different terms, such as structured English, pseudocode, and flowcharts.